So, in particular I know that, so I know that the Borel sigma algebra on R2 is generated by semi infinite rectangles, right. So, since sets of the form minus infinity x cross minus infinity y are Borel on R2, P x y of that guy is well defined. Correct. So, it is defined for all Borel sets. So, it must be defined for the generating class, right. I mean I am repeating the same argument I did for single dimensional one dimensional case, right. Okay, and this is called the joint CDF, joint cumulative distribution function. Okay, this is, we will denote this by f x comma y of little x comma little y, which is the probability law assigned to these semi infinite rectangles. Okay. So, this is, to write it out fully, this is the probability of omega for which x of omega is less than or equal to little x, and so I should really write x of omega less than or equal to little x intersection omega for which, so I should really write this, right. So, I will never write this again, just for once I will write this, I will abuse notation from now on. So, I should write correct. So, but this is what I mean, this is abbreviated as probability of x less than or equal to x comma y less than or equal to y, again abuse of notation, a serious abuse of notation, but this is what I will write from now on, but whenever I write this I actually mean this. Okay. This is called joint CDF. Okay. With me?
So, you said from joint probability law we can get individual probability law.
Yes.
But is it possible individual probability law, from individual probability law we can get joint probability law, because the probability measure is defined as sigma of
No, you cannot do that, I mentioned this earlier. If you are given this p x y, the joint probability law, you can clearly get individual probability law by putting one of them to be R, right, the other you keep whatever Borel set you want. But if you are given the separate probability laws p x separately and p y separately, you may not be able to figure out what the joint probability law is, can't be done in general. In fact, in the example I gave, right, the omega and 1 minus omega example I gave, if you give me the separate probability laws, they will both be uniform, but the joint law is not a uniform measure on the unit square. Okay, you just think about what I just said. Okay, the example I gave on, you take sample space as the 0 1 interval, you take x of omega equal to omega and y of omega equal to 1 minus omega, okay, and the separate probability laws will be uniform on 0 1 for both cases, but giving p x and p y separately will not give me p x y. Okay.
in the Lebesgue measure, is it possible because px of a and px of b is given, we can use pxy is a multiplication of the both, because it is a interval.
No, but p x may not be Lebesgue measure, right, I mean, so p x y may be some arbitrary measure, right.
Lebesgue measure is possible.
For even if p x and p y are separately Lebesgue measures, the p x y may not be the Lebesgue measure on R2, that is exactly the example I am giving you. Okay. Okay, so far okay. So, now again, so this is a complete intellectually it is a complete repeat of what I said in R. Okay. Actually people do not, I mean you can do all this on Rn and just forget about it once for all. Okay. So, now what am I going to say? So, if I give you the probability law, I can specify the CDF like I have just done. The question is the opposite true? If I give you the joint CDF, is it true that I can generate the joint probability law, because this is what completely specifies my my statistical properties of x and y together, right? What do you think? Why? It is a pi system, right? So, this defines my measure on the pi system on R2, which is these semi infinite rectangles, and you know that from the theorem we stated but did not prove that if we specify a measure uniquely on a pi system, it gets uniquely specified on the sigma algebra also, right, correct. So, the joint CDF uniquely specifies the probabilities of all Borel sets on R2, fine. It is because of the pi system theorem we derived. You can make a note of that. As I said, everything is a repeat, right. So, I do not this class is a total repeat except for the first few things I said. So, okay. So, I have started stating some properties of the joint CDF. Most of these are along the same lines, I mean along expected lines, if you know the probability of one dimensional CDFs. So, you are looking at two random variables. So, we will always use this notation, okay, capital F and indexed by the random variables capital X comma capital Y. If these were x1, x2, x3 or whatever, you will write x1 comma x2 comma x3, and the arguments are these guys, x less than or equal to whatever, right. So, as you would imagine, so this is a function of two variables, right. So, you should look at the plot in 3D, right. So, when x and y both go to infinity, the joint CDF goes to 1, and when x and y both go to minus infinity, the joint CDF goes to 0, okay. You will again prove this the same way, okay. You can show using continuity of probabilities, okay, just like we showed it in the one dimensional case. So, one remark here is that when I write something like this, limit x tending to infinity, y tending to infinity, I mean that x and y can go to infinity along any trajectory in any order. So, normally I should write limit x tending to infinity, then limit y, or in some other way, right. So, when I write limit x tending to infinity, then a limit y tending to infinity, I mean that the inner limit goes first, right. But if I write something like this, I mean that it does not matter how these x and y go to infinity, right. You can go along any trajectory, okay. So, no matter how these what the trajectories are, this is limit is equal to 1. Similarly, no matter what trajectory along x and y go to minus infinity, this limit is always 0. Then you have monotonicity. F x y of little x1 little y1 is less than or equal to f x y of little x2 little y2. And this is again obvious because, so the set of omegas that map to less than or equal to x1 less than or equal to y1 is smaller than the set of is contained in the omegas that map to this semi infinite rectangle, right. So, this will follow. F x y is continuous from from above, i.e. f x y of x plus u y plus v, where limit u down going to 0 and v going down to 0 is equal to f x y of x y for all x y. See here, so here, so this here, this is a 3-dimensional function, right. So, you have to be a little bit careful. So, let me explain what this means. So, you are looking at, so this is your, let us say this is your x plane and this is your y plane, okay, and you are looking at what the CDF is doing coming out of the board, right. And you are saying that if you take any point here, all right, and if you approach this point from above, meaning that, so your v, so your u is your x variable, isn't it? Yeah. So, your u is coming like that and v is coming like this, right. So, if you just imagine a axis here, so your u and v can approach 0 in any order or any rate, but they have to come down to 0. So, you can either have this go to 0 first and then that go to 0, right, or you can go on whatever trajectory you want, right, you can do that, right, you can do that, right, u comma v can go to 0 any whichever way you want, except you cannot do that or do that, right, you should not approach like that or approach like that or approach like that, right. So, as long as u v approach to 0 like that, you have the limit will be equal to the functional value, which is what continuity from above means, okay. This is the equivalent of right continuity in 2 dimensions, okay. So, both u and v have to approach from the positive coordinate, right, never going to any of the other coordinates, right, then you are okay, then this limit will hold, okay. Again this follows from what result? How will you prove this? Continuity of probabilities, right, you consider any sequence u n going to 0, v n going to 0, going down to 0, and you just write it out and you will apply continuity of probabilities, okay. Everybody with me? Finally, I will put one property which this is all basically a repeat of what we said for one dimension. So, I will just put one property which has no corresponding equivalent in one dimension, because it talks about the marginal limit. So, if you have f x y of x y, you send y to infinity, you should get the marginal of x. Y to infinity, you should get the marginal of x. And similarly, if you send x to infinity, this is true for all x, this is true for all y. So, what this is saying is that if you send one of the arguments in the joint CDF to infinity, the function you get will be a function of the other variable, and that function will happen to be your marginal CDF of x. See, the marginal CDF is nothing but the CDF of x, okay, except when you have two variables, you will call the CDF of one of them as a marginal and call this as the joint, right. This is your familiar old CDF of x, which is this probability that x is less than or equal to x. Similarly, this is probability that y is less than or equal to little y. Again, the proving this will involve, sorry, you should use some continuity of probability result. You will fix an x and send y to infinity along some sequence, and you will end up with probability that x is less than or equal to x. Okay. So, given the joint CDF, I can determine the marginal CDFs, the separate CDFs of x and y, but the opposite is not true, right. Given this and given that separately, there is no way to figure out the joint CDF, right. In fact, given you can show by counter example, right. You can take two CDFs, marginal CDFs corresponding to two different joints. If you can construct even one such example, you have proved that given these two you cannot reconstruct this, but of course given this you can reconstruct the marginals, right. Essentially the marginal only captures the statistical behavior of that random variable, whereas the CDF will capture, as the name says, the joint distribution, right, which is it captures the interdependent structure between x and y. Any questions?
Can we define the conditional CDF? It's conditional.
We will define conditional CDFs later. Okay, I will stop here.